Okay, lecture 74, orbits, or why the Earth doesn't fall into the sun. Okay, so let's start with thinking of a little, what do we call this, a ditch, I guess, with frictionless walls, and I've got myself a little ball, and I pull it up to some height, h, right? We call this height here h, right? And I let it go. What's it going to do? It's going to roll down the hill and back up to the same height that we let it go at, right? Why does it do that? Well, conservation of energy, right?
Yes.
So as the ball is rolling along, so the potential energy, right, is of course, you've got U is mgh, where h is the height, g is the acceleration due to gravity, m is the mass of the ball, right? So when we started out, it has no velocity, right?
Yeah.
And then it starts rolling down the hill. When it gets to the bottom of the hill, that's what we're going to call the potential energy equal to zero. Okay? We always have the liberty to choose the point at which we set the potential energy equal to zero. That's kind of like moving a ruler around, right? You have freedom to move the origin wherever you want to, right?
Yeah.
So we can do that with potential energy as well. So we'll call this zero, so we measure h from the bottom of the well, or the bottom of the ditch, I guess. When it's at the bottom, its potential energy, right, will be at its minimum value, but its kinetic energy will be at its maximum value, right? You can just imagine the ball is going to pick up a lot of speed as it rolls down the hill, and it'll be going fastest here at the bottom, right? So when it's at the bottom of the hill, right, we've got V max, right? And so that's when everything is in terms of the kinetic energy. Ke, sometimes you write it as T. That's 1/2 the mass of the ball times the velocity squared, right?
Yeah.
And then it starts climbing back up the hill again, right? If it's got this much kinetic energy, right, it can exchange that kinetic energy for potential energy, right? And that's the way we think of it. And so we say that the total energy, E, is conserved, and that's the kinetic energy plus the potential energy. Yes?
Yes.
We've talked about that before. So if we now imagine, here's a way to think about this. If we think of just the potential energy part, right, and I make some axes here, there we go. And I say, here's U, here's X. That's the distance that we've traveled, right? We've gone from, say, X equals 0 all the way over to here to X equals, I don't know, L or something, right? L. So then we go out here and then we come back. We can think of the potential energy function, U, as being something we can graph like this, okay? And in general, if we have a potential energy function, we can think about the dynamics of the system as if it were a ditch like this, okay? So just as a kind of a hypothetical quiz, if I said that the potential energy as a function of distance looked like, say, this, and I said that you're located right here, what do you think would happen if this thing gets bumped just a little bit, if I give it a little bit of kinetic energy?
Roll down.
Its potential energy's got to go down, right? And what's going to happen then, right? It's going to roll down the hill, right?
Yeah.
So you can think of this as like a marble on top of a little mound, right? It's not very stable up there. It's not very stable up there, right? And so any little bump and it's just going to roll right off, right? As opposed to, say, this situation, if my potential energy function looked like this, and I said we're down here, right? And if I give it a little bit of kinetic energy, what's it going to do? It's going to, roll up to some height, right? And then roll back down, right? So it's going to roll back and forth inside this well. Yes?
Yeah.
Okay. So let's look at, last time we talked about the gravitational potential energy, and I gave you guys a fairly simple derivation for the gravitational potential energy based on Newton's universal law of gravitation, right? That the force is equal to big G, which is just a constant proportionality, times the product of the masses, divided by the square of the separation between the bodies, right?
Yeah.
And we found that that potential was U equals minus G, call it big M, little m, over R, right?
Yes.
And if I were to graph this, I'm only going to consider positive R values, okay? Because we can't be negatively separated from the body. Call this R, call this U. What does this function look like? Well, this function looks like this. Asymptotically approaches 0 as R increases, right? And so you're thinking, well, all right, let's use that ball analogy and imagine that this potential energy surface that I've drawn here is something that a marble is sitting on. Anywhere that my marble sits, right, it's always going to roll down the hill, right? That's equivalent to, the Earth falling into the sun, or the moon falling onto the Earth. And so the question is, why doesn't it do that? Well, we know why it doesn't do that. We had this picture that Newton gave us of, a cannonball being launched from a mountain, on top of the Earth.
Yeah.
And if you launch it with enough velocity, then the surface of the Earth will always curve under it, such that it'll fall forever and just keep going around and around and around. We call that an orbit, right?
Yes.
And so that's fine. You've got that picture. You understand it's because these bodies are moving, right? The moon is moving. It has a velocity, right, that is tangential to, the line that connects the moon and the Earth, right?
Yeah.
And so it's always falling around the Earth, just like Newton's cannonball, right?
Yeah.
And the same thing is true for the Earth and the sun, okay? But why doesn't our mathematics show that? Why don't we see this in this potential energy surface? If I look at this, I say, well, doesn't matter what you do, you're always going to roll down the hill and fall into the sun or the Earth or whatever big M is, right? I think you already understand why it doesn't fall into the Earth. It's because it has some velocity. It has angular momentum, right?
Yeah.
It's orbiting around the body, the sun or the Earth if it's the moon, right? But how do we get our math to show us that? And I'll show you that today. It's actually pretty straightforward. Okay, first, remember from lecture 62 that this kind of, call it the energy of angular momentum, right, was 1/2 I omega squared. Do you guys remember that?
Yeah.
So I is the moment of inertia. It's kind of analogous to the mass of a body. Omega is the angular velocity, and that is analogous to linear velocity. So this is just like the kinetic energy formula, 1/2 mv squared, right?
Yes.
So if I were to write down for, an orbiting body what the total energy is, I would say, well, that's easy. It's just the kinetic energy, 1/2 mv squared, plus the potential energy, whatever that is, right? And we know what that is. That's this potential energy that we derived in the last lecture, right?
Yeah.
Inside this kinetic energy term, though, we can think of the velocity being broken down into two components, right? It's the component, here's maybe the sun, and here's, say, the Earth, right? And it's orbiting, right? And it'll have a velocity which is kind of tangential to the line that connects them, right? So here's our orbit, right? We know it's going to do something like this. I'm not going to draw the whole orbit. And it's got a velocity in the direction of r, the separation between them, right?
Yeah.
Because here, the distance from the sun is a greater distance than, say, it is when it gets here, right?
Yeah.
So you can see that when r is here, it's actually less, right? So we've traveled in the radial direction a little bit. So we can break this down into two components. We've got a radial velocity, which I'm going to write as v sub r. Okay, so that's when we get closer to the sun. The rate at which we get closer to the sun, that's that radial velocity. The tangential velocity, you might recall, right, is basically built into this. So we're going to have plus 1/2 I omega squared, and then plus the potential energy u again. Okay? So we're breaking the velocity down into these two components, this tangential component, which manifests itself in terms of this angular momentum energy that we talked about in lecture 63, I think, 62, and the regular linear kinetic energy, okay?
All right.
So I can manipulate this a little bit. But first, I want you to remember from lecture 68 that we talked about the conservation of angular momentum for an orbit, right, or circular motion, really. Okay?
Right.
So if we're moving around in a plane like this, why does it never leave this plane? Why is it always in this one plane? Why couldn't it go up a little bit or down a little bit? Well, of course it could, but there's no preference, right? There's no reason why it should go up or down. And since there's no preference for either direction, it always stays in the plane. And this we showed in more mathematical detail in lecture 68, right? That the angular momentum is conserved, which means that L, the angular momentum, is constant, okay? So we have this, let me just write lecture, this was 62, and then from lecture 68 we had that L equals a constant, okay? Well, that's convenient because what I want to do now is relate I omega squared back to L. And we can do that because L, the angular momentum for this orbiting body, is equal to the mass times the radial separation squared times omega. And so if I solve for omega, right, what does that mean? That means that omega is equal to L over mr squared. If I call this equation 1, I call this equation 2, I can put 2 into 1, and I can get that the total energy is equal to 1/2 mv sub r squared. That's just the kinetic energy for changes in the radial direction, plus L squared over 2, I'm just substituting in for this, 2mr squared. And then, of course, plus U. But remember, U is the gravitational potential energy, so I'm going to write this as minus big G, big M, little m over R. And so now, if I just focus on this part right here, if I recall this the effective potential, right, then what would I have? I'd have something that looks like a kinetic energy plus a potential, right?
Yeah.
And if I graph this effective potential, what's it going to look like? Well, I didn't leave myself a lot of room to graph it, did I? I'll graph it over here. That's it. So this is R, remember? This is, I'm going to call this U effective. But I'm going to draw, in a dotted line, I'm going to draw, well, actually, let me draw what it looks like. If you plug this in, right, this is something 1 over R squared minus 1 over R, okay? And if you go to like desmos.com or something like that and you graph 1 over R squared minus 1 over R, you're going to get something that looks like this. And if I compare this with the original, just the minus big G mm over R, that would basically look like this dotted line here. So see, here's the old potential that we looked at before, and we were like, well, hey, this doesn't look like it's ever going to be stable. It looks like it's going to fall into the planet or into the star, right?
Yeah.
But here is our effective potential that we've drawn, right? And you can see this has got a nice little ditch that we can roll through, right? And so what I want to do next is consider some of the possible orbits that you can get using this effective potential, which is this quantity here, okay?
Okay.
Okay. So if we choose the potential energy to be equal to this minimum, right here at the bottom of this ditch,
Yeah.
right? This corresponds to a circular orbit. Notice that it's not oscillating back and forth. There's no motion. There's no change in the distance from the sun, right? Or the gravitating body in this case, right? It's fixed. R is constant, okay? So there is no radial velocity direction, okay? The distance between the two orbiting bodies is not getting closer or farther apart from each other. This is a circular orbit. So this is what it would look like for a circular orbit, okay?
All right.
If instead I allow the potential energy to be here, then you can see we have these 2 points, right? And so what does this correspond to? This would be an elliptical orbit. Put the sun here. I'm going to call this, mark 2 points on it, right? We have the point where we're farthest away, right? That corresponds to this point here. This is called aphelion. And then the point where it's closest to the gravitating body, that's this point here. This is called perihelion. Okay, so you can see, you can think of the dynamics of this system as a ball rolling down the hill, and then back up, and you can even see it, right? When is it rolling fast? When is it rolling slow? It's rolling pretty fast here, right? It's a very steep curve here. This is not so steep, right? So it rolls down slowly, picks up speed, and then slows down to a stop, you see?
Yeah.
Back and forth and back and forth. So that's for an elliptical orbit, okay?
Okay.
The next one would be a parabolic orbit. That's when we let the energy be here. Somebody just write circular, elliptical, parabolic. That's when the potential energy, the effective potential energy, is equal to 0. Okay?
Okay.
When that's the case, we get something that looks like this. This is the sun, and we get a parabola. I guess that looks parabolic. I don't know. It's my best parabola. Okay?
Okay.
So in this case, right, it's like the ball is starting up here at 0, but remember, this asymptotically approaches 0, right? So it'll never get back to 0 again. So it rolls down the hill real fast, and then moves away slowly forever. It's never going to get back up to zero again because, like I said, this asymptotically approaches zero. Okay?
Okay.
So we call this escape velocity. Okay? That's the minimum velocity you need to escape the gravity of a gravitating body. If you wanted to leave, like the solar system, something like that, you need to achieve an escape velocity with respect to the sun. If you want to simply leave the Earth, you have to achieve an escape velocity with respect to the Earth. Okay? Well, actually, we'll talk more about escape velocity, I think, in the next lecture. I think we're going to talk about that in some detail. And the last one would be, well, what if I give it a potential energy of, I release my ball from here, right? This will correspond to a hyperbolic orbit. And the difference there is not, kind of think of it as, we have these two lines that asymptotically, there we go. And that's a hyperbolic orbit. Also, it will never, it's not bound, right? So both the parabolic and the hyperbolic orbits are not bound states. Well, that's quantum mechanics, sorry. They're not bound systems, okay?
Okay.
The bound systems are the circular orbit and the elliptical orbits, okay?
Okay.
The parabolic and hyperbolic are unbound, right? So they will escape. And that is basically the easiest way to think about these orbits. And it answers the question, mathematically, why is it that, how do we see mathematically that things don't just fall into the sun? Okay?
Okay.
And that's how we do it, using the effective potential. Okay?
Okay.
That's it.